Hello everyone, thanks for attending this talk. Today I'm going to talk about how to build a correct by construction FHE model. My name is Wen. This is joint work with my colleagues from Intel Labs. And Zhengkun is also here today in the meeting or conference. So for today's talk, I will start by explaining why we need a new approach, especially in the FHE scenario. And I will talk about the challenges we face in maintaining the functional correctness in running these programs. And then I will give you a very high-level introduction about the major technique behind our work, which is formal verification and Dafny. And then I will present you the approach and further how to use the correct by construction approach to build the FHE model. And then I will give you a deep dive into a case study, which shows you actually how to use a Dafny to construct a model for the Montgomery reduction algorithm, which is actually the algorithm we use in our actual work. And in the end, I will discuss briefly what we're currently working on and what we have in mind for next steps. So let's first take a look at what it actually takes to implement an FHE program on a real-world system. You can see on the left hand, you have an FHE program, and on the right end, you have the system, right? It can be a pure hardware, software, or it can be more complicated hybrid platforms. So to actually map the program into the system, you have to go through, I would say, a relatively complicated flow, the decomposition flow. You first have to decompose the program into a sequence of FHE operations, and further, because these operations are oftentimes defined with very complex arithmetic or very large data fields, you want to apply optimizations. For example, you want to convert it with the residue number system and use this new data representation. And at this level, you have to handle with the polynomial arithmetic. And further, you can implement polynomial arithmetic through modular arithmetic. And in the end, you can start mapping it to a system. So this flow naturally brings challenges. So what are these challenges? First of all, you can see you just have to jump between different data representations, and this involves transformations. And another very interesting point, and I'm not sure you guys have thought about it before, is for implementing specific operation, right? You always have to choose an algorithm and then use this algorithm as a reference in your implementation. But have you thought about, how do you make sure that your reference algorithm itself is correct? So that's another challenge that we face. Furthermore, especially in the FHE setting, we always want to run the program a little bit faster, right? So we want to apply optimizations either from algorithm level or it's more platform-specific optimizations. And this naturally brings the research challenge or research question we would like to answer through our work, which is after applying all these transformations, all these algorithms, all these optimizations, how can we make sure that the FHE program is still running functionally correctly? So that's a question we would like to answer. Well, one solution can naturally be program testing, right? Which I believe many of us use a lot in our work. And how does program testing or validation work, right? It's a simulation-based approach. The idea behind it is very intuitive. You have a system which is under test, and then you give it some input. It's your stimulus for a system, and then you observe the output and try to reason about it. Does it make sense to you or does it not? So pretty straightforward. However, there is inherent limitation in this approach. And why do I say that? That's not even mention the FHE case, right, in the testing scenario, because I would say perhaps there are millions of free variables in the input space, right? Let's just say modern crypto, a SHA-2 algorithm or something, where the input space may involve a few hundred or a few thousand of bits. And even in this scenario, it's simply not possible to cover the full input space. And the reason behind it is easy. Suppose you have a size n input space, you have to run 2 to the power of n tests to fully cover the space, right? And this is simply not possible. So how do we then, basically break this constraint and in the end actually achieve a convincing proof that my program is running correctly? So in our work, instead of relying on program testing to find bugs in our program, instead we rely on formal verification, which is a major technique we rely on. And this is a tool that can actually, in the end, give us a mathematical proof showing that my program is bug-free. There's no bug in my program. So how does formal verification work from a very high level? I'm not going to go into the details. So this is a pretty systematic approach. It's composed of 3 parts. You have, first of all, very importantly, you have specification, which specifies, okay, what is the intended behavior of your system? The second part is the implementation, which you would like to verify against the formal specification. And in the end, you should have a proof, a formal proof showing you the correctness. And what's the benefit of formal verification? I believe one of the selling points for formal verification is that it can easily cover the full input space without the constraint we faced through the testing-based approach. So hopefully this gives you a very high-level idea about what is formal verification. Now let's talk about the actual verifier that we use in our work, which is called Dafny. It's an automated program verifier. And just to give you a bit more background about Dafny, it was originally developed by Microsoft Research. And actually, it's not like the product of academia or something, right? It actually has been used to verify real-world software systems. Very good example would be, it was used in Project Everest, again from Microsoft. And the purpose of this project is to formally verify the HTTPS ecosystem, including TLS and many different crypto primitives. And I believe Amazon AWS is also a heavy user of Dafny, and it's used for security verification in its cloud services. So that's some words about Dafny. So how do we actually use Dafny to build a model? Again, 3 key components. First is the specification, where you specify, okay, what is my input? What is any parameters, any constraints I have to set, right? Precondition. And further, what is my output? And this is the post condition. And that's a specification. Further, we need the implementation, right? And this example here is a modular inverse example. And you can see that how we implemented it is actually pretty much what we would kind of prove that mathematically. Here you can see we actually rely on the extended Euclidean algorithm to find the modular inverse of the input. And you can also see there's also the proof part, which in the end will help us or help Dafny understand that, okay, your implementation actually matches the formal specification. So a very interesting point when we use Dafny is that also in the code, you can easily see that when we do the implementation as well as the proof, which is written Dafny, you can see that we pretty much adopt the same mindset as if we were trying to prove the algorithm with a pen and paper, right? Only that we just now have to write it in a way that Dafny can understand, can reason about step by step. And in the end, Dafny and the backend SMT solver can help us prove that if my implementation is verified or there's actually something wrong with it. So that's the overall idea about the Dafny tool that we use. Now let me show you the approach. But before showing you the approach, let's take a look at the conventional design flow and see what does the what are the limitations in this flow. And this should also be a pretty familiar flow to you guys. Now let's say I want to implement certain algorithm on my system, right? How do I do that? Well, oftentimes we start from a baseline algorithm. Let's say in this case, it's a regional FHE algorithm. And I want to optimize it. So I applied a bunch of optimization steps. And in the end, I get an optimized FHE algorithm. And further, I still need some manual process to map it to my system, right? In the end, I will have a real world hardware-software implementation. So pretty smooth flow. What's wrong with, why is there anything problematic, let's say? So you can see that oftentimes we apply optimizations. It can be algorithm level, architectural level, all kinds of optimizations, right? And oftentimes these steps, they're just informally tracked and they are just lost somewhere. There's no formal specification for that or anything. And in the end, we oftentimes rely on validation to test if my implementation on the system is doing something correctly. And this is based on validation, and we already saw what's the limitation in the validation approach, right? So in the end, it will lead to a pretty big gap between where we start from, which is the baseline algorithm, versus what we actually put on our system, which is the actual implementation, right? And why can this be problematic? Just imagine you run your implementation and all of a sudden something breaks. It's very hard for you to trace back and understand where it went wrong specifically. That's why we want to propose our new end-to-end, the so-called correct by construction approach. And the idea is that starting from the very baseline algorithm, we already start modeling it in Dafny, right? Of course, we have a formal proof showing that the algorithm is correct. It is proven. And then more importantly, for each and every optimization step, we will, again, use Dafny to model that and formally prove that through equivalence proof. In the end, we will get a new Dafny model, which is actually mapped to the optimized algorithm. And this model, again, it's formally proved. And then at this stage, we still want something that is executable, right? So one good thing here is we also have a Dafny compiler, which can generate the executable model. And it can be written in C++ or Python or some other languages, depending on the system that you would like to run your model on. So you can see that by the time you have some FHE program constructed, it's already proven to be correct. Then how do we use this approach to actually build an FHE model? Well, the idea is pretty straightforward. We already see the flow, right? So what we do is we start from the very basic level, which is the modular arithmetic, and you build a Dafny model for this level. And once this part is formally verified, you just treat it as a black box and then use it to build a Dafny model for the higher level arithmetic. And in this case, it's the polynomial arithmetic. And all of the transformations for you to go from one level to another, right? It's all taken into account in our Dafny model. And then you can just apply the same idea, and in the end, you will get a Dafny model, which is mapped to your actual FHE program. So now let's recall the challenges we showed at the very beginning of the presentation, right? So when we map FHE programs, we have a bunch of challenges, right? We need to transform between different data representations. We want to make sure that reference algorithm is correct, and further, I want to track all of the optimizations I apply. So you can see that with this construction approach, as well as the FHE model construction strategy, you can see that everything is taken into account when we construct the model, right? Sorry. So naturally, you can see that all of these challenges will be smoothly tackled by following our strategy and approach. And we can confidently say that in the end, we will achieve a formally verified FHE program, which is guaranteed to perform correctly on the system. Okay, so hope this makes sense. Now let me give you a little bit more flavor about a Dafny model. And here on the top, you can see this is a pretty standard algorithm, the Montgomery reduction algorithm. And in the lower part, you can see an actual Dafny model, which is longer than the modular inverse example. So you can see the algorithm is pretty straightforward, right? Just 3 lines, pretty much. And we all know that Montgomery reduction is used for us to eliminate the actual Montgomery factor after we do multiplication in the Montgomery domain. And that's the high-level idea, right? So how do we actually prove this baseline algorithm in Dafny? Again, you can see there are 3 components. First, you have specification, right? You have to specify you have to specify what is my input, what is my auxiliary parameters, right? And in the end, what is the output? And also, very importantly, the implementation part, right? Which is denoted by the blue boxes here. Very interestingly, again, you can see that the implementation is very similar to the algorithm description. It's pretty much how we would prove that by hand. And how does the implementation work? Well, first we have to compute M, right? The exact same M, which is specified in the algorithm. And then after M is computed, you want to multiply it with the modulus M and add it to your input T, right? And you further divide it by R, which is the Montgomery factor. And in the end, you may need 1 extra correction step to bring it to the final result. So that's pretty much the implementation, pretty straightforward. And what about the proof part? Proof part, from my point of view, is the really interesting part. You can see there are 3 components. One is the divisible proof. When you actually add M times N into your input, you want to prove that it is divisible by R. So that's what divisible proof does. And another very interesting thing and very important thing we want to prove is the range proof. And what does that mean? Basically, after we compute T, we want to prove that T is actually a pretty small value, and further, it is within a certain range. And this is pretty much what the range proof part is trying to prove. And in the end, we also have the congruence proof, which is to show that, okay, my final result is correct. And more importantly, it actually matches the result specified in the specification. So that's pretty much a complete Dafny model, a complete proof for the baseline Montgomery reduction algorithm. And you may wonder, well, this is a pretty well-known algorithm. Why do I want to prove that, right? The reason is oftentimes we don't use the baseline algorithm for implementation. We use the optimized version, right? So what we do in our work is based on this baseline algorithm, we went ahead and applied optimizations. First step is we actually built a Dafny model for the multi-precision version of the Montgomery reduction algorithm, or what we call the word level version of the algorithm. And further, we also integrated the entity-friendly prime optimization into the model, also the proof. And we do this step by step. And in the end, we actually have a formally proved optimized Montgomery reduction algorithm. And this is actually the exact algorithm we use for our actual work. So hopefully this gives you some idea about how to use Dafny. Sorry, to prove a very interesting algorithm. Now let's briefly talk about what we're currently working on and what we have in mind for the future. So at this stage, we are pretty much done in building model for the modular arithmetic. And we are currently working on the polynomial level of the arithmetic. For example, we are actively working on the NTT or number theoretic transform algorithm modeling and proof. And together with other polynomial arithmetic is built, we will go ahead and build the FHE operation level of the modeling, and in the end for the FHE program. So that's exactly the focus of our work, right? In the end, we want to achieve a correct by construction FHE model of program. And actually, an interesting thing I want to bring up is, as you may already get from the presentation, right? There's nothing in our approach that is FHE specific. With that being said, it's basically that we can also apply the same correct by construction approach to other cryptographic algorithms or programs as well. And in the future, hopefully, we can achieve the so-called correct by construction cryptography. Okay, so with that, it concludes my talk, and I'm happy to take questions if there are any.